So Newton and Leibniz were both working on calculus here, and they're both kind of credited with these theorems that we're going to talk about. The first one being the fundamental theorem of calculus, and as it sounds, it is the fundamental theorem of calculus. Like this is your integration at its finest, pretty much. You don't want to forget your ways to approximate it, because you're going to come across maybe some integration that you can't do with shortcuts, and so you want to be like, okay, there's another method that I can do if I need to. And so the first method that we did, you would use if it was something that maybe you could not do a shortcut and an antiderivative for. But as we get into antiderivatives, you're going to find some pretty complex functions that you can actually do antiderivatives for. So we do learn the long way, and then we're going to learn the shortcuts, which is this. So this theorem says that a function is continuous on a closed interval. Obviously, you can't find area if the interval's not closed. And f is the antiderivative of your original function on the interval AB. Then you can take the antiderivative, right? So we have this function. We take the antiderivative. We plug in our top limit and get an answer. And we subtract what happens when we plug in our bottom limit, okay? And so that will give us the area of the space under the curve, is what we're looking for. All right, so this breaks it down. Guidelines for finding it. You want to, provided you can find an antiderivative, that's key. If you can't find an antiderivative, you're going to have to use another method, right? But provided you can, then a little bit of notation that I want you to see. The first notation is the basic antiderivative notation. But watch the notation change. This notation means I have not yet taken the antiderivative. It is telling you to integrate, okay? This right here is telling you take the antiderivative, integrate the function. That's what that means. Then you'll notice over here, you have a capital F of x. This is the function that you found by integrating this one, okay? And so your bottom and top here are on the bottom and top of your integration. And over here, you see this little, what looks like the side of a matrices, if you remember a matrix, right? And then they have the top and bottom. So this means I have integrated, but I have not yet plugged in my B and A. Okay, so this just means I've done it. Now I'm going to plug in these two numbers. All right, the reason this is important is because there are going to be times when you're using some substitution, and you can substitute first and change your bottom and top cap. And so you always want to be aware of what am I now plugging in, okay? And that's why they do that second notation there. Once you have this, you literally just plug it in. So they did this guy as an example, from 1 to 3 x cubed dx, all right? This just means we're taking the antiderivative with respect to x. How do I take the antiderivative? Well, I add 1 to my exponent, x to the 4th, and I divide by 4. Now, normally I would have a plus c here, but anytime you have a top and bottom, you no longer need the plus c. This is not indefinite integration. They have a definite description of what they want you to do from A to B, in this case, from 1 to 3, okay? So now that we have taken the antiderivative, we're going to plug in the top number, the 3 to the 4th over 4, minus 1 to the 4th over 4, all right? That's 81/4 minus 1/4, that's 20. This is actually the same exact problem you had from homework, just different end caps, yes? Ooh. Wasn't that easier than homework? I'm just saying. So if we went back to our homework and we did this guy from -1 to 1 of x cubed dx, we would get x to the 4th over 4 from -1 to 1. 1 to the 4th over 4 minus -1 to the 4th over 4 is most definitely 0. We're going to do these. The first thing we're going to do is take the antiderivative. So x squared, what's my new exponent?
3.
Over 3, right? Minus 3, and now I have x, right? And I'm going to go from 1 to 2. So when I have something like this, think about the fact you have to plug the 2 into both x's. So this first group is going to be 2 cubed over 3 minus 3 times 2, all right? Minus what happens when I plug in a 1. 1 cubed over 3 minus 3 times 1, all right? And so then I am going to say 2 cubed, that's 8 over 3 minus 6, right? Minus 1 over 3 minus 3. So This is going to be 18 over 3. This is going to be 9 over 3. So 8 minus 18 is negative 10 over 3. Minus 1 minus 9 is negative 8 over 3. So I'm going to get negative 2 over 3. All right, let's look at the next one. This is 3. So I still would rewrite this first, 3x to the 1/2, right? And then I'm going to do my antiderivative. So my new exponent is going to be add 1, so 3/2. And then multiply by 2/3. The 2/3 and the 3 will cancel, and I just get a 2, right? Okay. And then I am going to do that from 1 to 4. All right, so we're going to say 2, 4 to the 3/2 minus 2 times 1 to the 3/2. 3/2 is just square root cubed, right? So the square root of 4 cubed is 8. So 2 times 8 is 16 minus 1 to any power is 1. So that's easy. So this guy is 14. Now you do have to know your trig functions. The antiderivative of secant squared is tangent. All right, so we have tangent of x from 0 to pi over 4. They were very nice to us. The tangent of pi over 4 is a very easy one, right? That is just 1 minus the tangent of 0, which is also nice and easy. This whole thing is just 1 minus 0. Let's look at absolute value. So here's the thing with absolute value. Absolute value has a turning point, right? If you see this graph, like any absolute value, it's going to be a V. And so if you cross over the vertex of it, then how you actually do it is going to change, because one side of the vertex is going to be positive and one side is going to be negative, right? You have a negative slope on one side, a positive slope on the other. So you have to decide where this guy is positive and negative, and you have to negate it because absolute value is always positive. All right. And so when you're doing an absolute value, the first thing you're going to do is say, within my range, within my A and B from 0 to 2, does this guy turn negative, right? The best way to figure that out is say, well, it's greater than or equal to 0 or less than or equal to 0, like one or the other, right? And so if you find out where it equals 0, then you can figure out what you're going to do with it. And so the first thing I'm going to do here is I'm going to set this guy equal to 0, and that's going to be x equals 1/2. So we know at 1/2 is the point where it equals 0. So at one point, it's going to be greater than 0, and at one point, it's going to be less than 0, okay? And so if I look at this, I would say, well, if I plug in something smaller than 1/2, like if I had made this, where is this less than or equal to? You would see that less than or equal to 1/2 is where it is less than or equal to 0, right? Because if I put in, let's say, 0 is less than 1/2, right? My equation is going to be negative. 0 minus 1 is negative, right? And so from 0 all the way up to 1/2, this absolute value function inside of it would be 0, would be less than 0, right? So from 0 to 1/2, I would have a negative number inside of there, right? Does that make sense? But this is absolute value. I need it to be positive. So the only way to take a negative and make it positive is to multiply by a negative, okay? So what I would do is I would say, well, from 0 to 1/2, I'm actually going to negate what happens here because I want it to be positive. And any number from 0 all the way up to 1/2 is going to give me a negative number. But they're telling me this is absolute value, which is always positive. So therefore, I have to force it to be positive, all right? But then from 1/2 until 2, any number between there is actually going to already give me a positive number. 1, for example. You plug in a 1, 2x minus 1 is positive, all right? If my x is 1. So I don't have to negate this group. This group is already going to be positive. So I'm going to leave this group completely alone. So anytime you have an absolute value, you need to figure out if setting it equals to 0 happens within the range that they gave you. All right? Because if within the range that they gave you is a negative, you're going to have to negate the whole thing because it is absolute value and it must be positive. So typically for an absolute value, you're going to split it up into two different ones. All right, you're going to do one before and one after. And it doesn't always, it could be an upside down, like it doesn't always negative first then positive. You have to figure out which group gives you a negative, which group gives you a positive. All right. And once you've done that, then you're just doing your integration the way you normally would. I would go ahead and distribute this negative 2x plus 1, and then do my integration. So my integration here, my new exponent is going to be x to the second power. When I divide by 2, I just get that -1 in front of it. And then I have a plus, 1 just becomes an x, and I'm doing that from 0 to 1/2. And then I'm going to add to it, this is just going to be x squared minus x from 1/2 to 2. And I'm just going to do those individually. All right. For this first one, it's nice because when I plug in the 0, it's going to 0 out. So I have -1/2 squared plus 1/2, and then that's going to minus 0. All right, so that's easy. All right, and then over here, I'm going to have 2 squared minus 2, and then subtract from that 1/2 squared minus 1/2. All right, so far so good. This guy becomes -1/4 plus 1/2. This becomes 2 minus 1/4 minus 1/2. All right. This is 2/4. So -1/4 plus 2/4 is just 1/4, right? Everybody see what I'm doing with my fractions? All right. And then this becomes 1/4 minus 2/4. So this is -1/4, but I'm subtracting it. So I have, all right, so this is -1/4, 2 minus a -1/4. So this is 8/4 minus a -1/4. So that is 9/4, 10/4, 5/2. Yeah, this is minus a negative. So here we have something that looks much larger. They gave us so I want you to look at the verbiage of this question, all right? Because here's where sometimes we struggle. If I hand you just, here's an integration problem and here's your boundaries and go with it, you can regurgitate that. But this problem's worded differently. It says, find the area of the region bounded by the graph, all right? That's my curve. The x-axis, so that's what we typically stop at, and the vertical lines 0 and 2. All right, so what have they given me? Well, they have given me my function, 2x squared minus 3x plus 2, all right? And they have given me my boundaries, okay? But they wrote it out versus actually saying this piece of it right here and handing it to me, okay? So make sure that you know how to interpret this statement into this problem. And then you really don't have too hard of a problem to do. At this point, I can just do what I've always done. My new exponent is going to be x cubed, and then I'm going to take that divided by that. My new exponent here is going to be squared, and then I'm going to take that, and then that's going to become 2x, and I'm going to go from 0 to 2. What's nice when you start at 0 is, what am I subtracting? 0 plugged into everything, so it's a 0, right? So I can just plug in my 2, really. So 2 over 3, 2 cubed minus 3 over 2, 2 squared plus 2 times 2, right? And then you're just simplifying. We have 8 times 2, so we have 16/3 minus, we have 4 times 3, so 12/2. I'm going to actually actually go ahead and make him smaller because we can just use 3 at that point. So we will say that is what, 6, and then plus 4, all right? If I did this in thirds, -6 plus 4 is -2. So I have 16/3 minus 2/3. Put it all to, minus 2 over 1. That helps to actually put that as over 3. So this is going to be 6 over 3. 16/3 minus 6/3 is 10/3, and I am done. derivative, second fundamental, if we have time. We talked about average value before, and we talked about mean value theorem when we talked about derivatives. Average value function, if you can integrate it, then the average value is going to be the integration times 1 over the difference between the two. So like I were to do this particular function, I would just take the antiderivative of that, just like I would. But I would multiply it by 1 over 3, 1 over 4 minus 1. So I take my final answer and divide by 3. Divide by the difference between the two, okay? So the average value does exactly the same thing. You just literally get, so when you do this integration, you get something like 48. But then you have to multiply by that 1/3. So the average value over this is going to be 16, even though the total, so if your total area is 48 over 3 units, then the average value for each unit is 16. That's all it's saying, okay?
How did you get the 1/3?
You took these, 1 over b, that's your 4, minus 1. So whatever your interval is, you're going to subtract it, which makes sense. If your entire area is 48 and it's over 3 units, then the average per unit is going to be that divided by 3. That's literally all you're doing. It's, think about the word average. How many units do I have? I went from 1 to 4. I have 3. So if I want the average, I would take my total, 48, divided by how many I had, 3. That's all it's saying for average value. So when it asks for average value, it's literally taking the entire area divided by how many units you have moved in that interval. All right? This is actually pretty straightforward as well. The second fundamental theorem of calculus says normally we're going from a number to a number. You can go from a number to a function, which seems odd. But really when this happens, you end up just plugging your function into it. So you end up just doing exactly what you would do. They give this first example here. If I am looking at to evaluate this function from 0 to x, well, I'm going to do the antiderivative of this guy, which is the sine, right? Antiderivative cosine is sine of x, and I'm going to go from 0 to x. All right? And so when I do that, I just plug in an x. Well, of course, that's sine of x. Then I plug in a 0. That's sine of 0. Well, the sine of 0 is 0. So I just get the sine of x. So you end up just taking the antiderivative of it. And this was technically a t, by the way. You end up taking the antiderivative of it and just plugging in your x. Now, I will say when it's something other than just x, you have to consider the derivative of the function. I know that sounds weird. But let's look at, we'll look at the example 8. You'll notice in this one, I go from a number to a function that is something other than just x, right? Well, my derivative of x is just 1. That's why it didn't matter. But this is x cubed. So this is a little bit different. This wants me to actually find the derivative of the function. Well, if I take the antiderivative and then take the derivative of the antiderivative, I go back to where I started from, right? So they're like saying, take the derivative of your antiderivative. Well, you don't have to go back and forth. The derivative of the antiderivative is going to be the cosine of t. Helps to write it correctly. If I want the derivative of the antiderivative, I'm going to get where I started, right? Now, if I plug in a pi over 2, I get a number. Well, when I take a derivative of a number, what happens to it? It zeroes out, right? So that's going to zero out when I take the derivative. So if I were to plug in my x cubed, I have the cosine of x cubed, but if I plug in my pi over 2, that's an actual number. The cosine of pi over 2 is an actual number, right? And when I take the derivative of an actual number, it drops off. So the number piece of it you can ignore completely. You end up plugging in this top guy, but you do have to consider the derivative of him because we have taken the derivative back. So think of it as the chain rule. I'm going to end up with him, but I also have to consider the derivative of the inside. And so when you take the derivative of an antiderivative, all your numbers just drop off, but your functions just get plugged in, which is what happened here. And you have to consider the derivative of that function. And so this ends up being 3x squared cosine of x cubed. So when they want us to take the derivative of the antiderivative, you end up where you started from, but you just have to plug in any function that's there, x cubed, and then take the derivative of that function, 3x squared, right? So it seems counterproductive to do the derivative of an antiderivative. If it's something, just a number, it's going to be 0. If it is a function, plug in your function and take the derivative of that function.